Next thing we want to look at is dimensionless pump performance. So the reason we're looking at this is to understand pump scaling. How do these different operating parameters change as we change the size of the pump, run it faster, or change other operating conditions like that? Now, we took the Buckingham Pi theorem. We're not going to do a Buckingham Pi analysis for this. We're just going to jump to the results. But the starting point for that would be as follows. Let's say if we were to choose head as the dependent variable we were interested in. Well, we would begin by saying head is a function of flow rate, diameter. This is that pump speed that I talked about. So N represents a pump speed in revolutions per minute. The density of the fluid that we're pumping, perhaps. Certainly the viscosity of the fluid we're pumping. And perhaps even a roughness parameter to characterize how rough the inside surfaces of the pump are. The scroll area and perhaps the impeller as well. So notice that the left-hand side, rather than just choosing H as the dependent variable, I'm choosing the product GH as the dependent variable. And this is a technique often used in dimensional analysis to force these two parameters to occur together. So rather than leaving H alone there and putting G in our list of parameters, we know ahead of time that the product GH is important because the pressure is rho GH. So G and H are always going to occur together. So we can force them to occur together by making that product our dependent variable instead of only H. So that's the little technique that we're using there. Well, if we were to take that and put it into our Buckingham Pi theorem process and turn the crank on that, we would get this. So notice here we have 1, 2, 3, 4, 5, 6, 7 parameters. They involve 3 fundamental dimensions, so we would expect 4 dimensionless groups to come out of this. And in fact, that's what we get. So our dimensionless head, GH over n squared d squared. So that's how we should be non-dimensionalizing head. And that's going to be a function of q over nd cubed, rho n d squared over mu, and epsilon over d. Now some of these are familiar. This is a relative roughness. And again, anytime we have two just geometric parameters in our list of independent variables, a ratio of those two is going to show up as a dimensionless group. So that's the relative roughness of the surfaces inside of this pump. This is a little bit more obscure, but this is actually a Reynolds number. Because notice the rotational speed times one of these d's gives a velocity scale. So this really is rho v d over mu, but the velocity in there is n times d. So that's really a type of Reynolds number. The other thing we could do, and again I haven't shown it here, is we could start this whole process over again, the Buckingham Pi theorem, only with shaft work over here instead of head. Because we're interested also, how does the shaft work depend on these quantities? And if we did that, we would get the same list of quantities on the right, and we would get the appropriate non-dimensionalization of shaft power. So W dot shaft over rho n cubed d to the fifth. So this leads us to the scaling laws for pumps. And these quantities that are showing up here have names. The ones we're particularly interested in are these 3. So those 3 are the capacity coefficient. So Q over ND cubed is called the capacity coefficient. Capacity referring to the flow rate that we can achieve. The head coefficient is GH over n squared d squared. So notice all these coefficients are dimensionless groups. And finally, the power coefficient, shaft work over rho n cubed d to the fifth. So the head coefficient and the power coefficient are both functions of the capacity coefficient. If we just go back here, notice the head coefficient is a function of the capacity coefficient, and of course these other things, Reynolds number and roughness, and the power coefficient is a function of the capacity coefficient and Reynolds number and roughness. So both of those things depend on the capacity coefficient. The efficiency is also a parameter of interest. Now, the reason I haven't mentioned efficiency in the dimensional analysis so far is that efficiency is already a dimensionless number. So efficiency doesn't have any units. It's already a dimensionless number. So let's see how it's related to those coefficients we already have. Here's our definition of efficiency. This is the so-called water horsepower divided by the brake horsepower. So that's the rate at which work is being done on the fluid, and this is the rate at which we need to supply work to the pump. So we can just substitute in. We're going to substitute in for our head coefficient. So this GH becomes the head coefficient times n squared d squared. Q becomes the capacity coefficient times nd cubed. And the power becomes the power coefficient times rho n cubed d to the fifth. Now if you look at this, rho cancels with rho. We have n squared there and n there, which is n cubed. So those cancel with that. And we have d to the fifth here because we have d squared and d cubed. So we have d to the fifth there and d to the fifth there. So it turns out that the efficiency is just the head coefficient times the capacity coefficient divided by the power coefficient. So when we're scaling a pump, if these three dimensionless quantities are kept the same, which the scaling laws say we should do, then that means the efficiency does not change. Really, you can just think of it as a fourth dimensionless group, so it does not change either. Because the head coefficient and the power coefficient are both functions of the capacity coefficient, the efficiency is also can be written just as a function of the capacity coefficient. Now we want to look at pump similarity. So we've identified these dimensionless groups. Let's look at pump similarity. Well, the capacity coefficient is Q over ND cubed. That means that if we have two pumps that are similar, we can relate their flow rates as follows. So the subscript 1 and 2 refer to these two pumps that are similar. So they're running at geometric and dynamically similar conditions. So the ratio of flow rates that we would get out of these two pumps is equal to their ratio of speeds multiplied by their ratio of sizes, characterized by the diameter, cubed. So two geometrically similar pumps, different size than each other, so these D's could potentially be different, and running at a different speed than each other, so these speeds could potentially be different. This will tell us the ratio of their flow rates. This is very useful information because if we know the performance of a particular pump, maybe pump 1 running at a particular speed, and we want to know what happens if we speed that pump up, or if we go and get one that is the same but is a different size, we can figure out what happens to the flow rate from this, from our pump similarity laws. If we're interested in the head developed by the pump, there's also a similarity law for that. So the ratio of H2 to H1 just comes from this. It's the ratio of the speeds squared and the diameters squared. And that's all coming just by setting this dimensionless group for pump 2 equal to pump 1 and then rearranging it to get the head ratio by itself. Finally, we'd also be interested in the power coefficient, which must be the same in the two situations. So the ratio of powers is the ratio of densities times the ratio of speeds cubed times the ratio of diameters to the fifth. So you can see that the pump size has a very profound effect on the pump power. It's raised to the power 5. So those are the pump similarity laws, and we'll be taking a look at those in an example or two later on. So I want to return to this idea of pump classification. This is a slide that we saw earlier when we were introducing this section, and it just shows the regions on the head versus flow rate space where different types of pumps are typically used. So we have positive displacement pumps here if we want to generate very high head at low flow rates. We have centrifugal pumps if we're looking at moderate heads and moderate flow rates, and then axial flow pumps if we're looking at higher flow rates but low heads. The last dimensionless group that I want to look at is something that helps us select pumps, in particular this spectrum here of centrifugal and axial flow pumps. So it's a pump selection parameter. We have a particular application and we want to select a pump that is appropriate for that application. So that is the idea of specific speed. It's kind of a funny name for a dimensionless group, but that's what it's given. So key thing to remember here, this is used for pump selection. We haven't yet selected our pump. We want to select an appropriate one. So we know our application. Okay, we know we need to provide a particular amount of flow, and we know we need to provide a particular head. So flow is determined by the requirements of our application. Our piping system will tell us how much head we need to provide in order to produce that flow. So we've looked at our application, we've looked at the piping system we're working with. We know the flow and the head that we need to produce. Typically, we also know the speed that we're going to be running at. Perhaps we have a particular electric motor available, but let's say that we know what speed we're going to run at. We could vary this and it would change the specific speed, but the premise here is that those three quantities are known at the beginning. So we want to take those three things and choose a pump appropriately. So what are we after when we choose a pump? Well, we want to decide what design should we be going for. Should we be going for a radial flow pump? That's what we've been looking at in detail, where the flow is in the radial direction, also called a centrifugal pump. Or do we want to move further to the right on that pump performance space and pick an axial flow pump? Or do we want a mixed flow pump? And a mixed flow pump is just a blend of the two. So which one of those styles of pump and how far along that spectrum should we be with this particular application? The other thing we want to know is how big should it be? What's the general size of a pump are we going to require in order to meet these requirements? So then we can go shopping for the right style of pump and the right size of pump. So this is what specific speed does for us. Now we need to figure out what kind of a parameter can do this for us. So what we want to recognize first of all is that we're interested in the characteristics of this pump at its best efficiency point. So here I'm showing the head coefficient and the capacity coefficient, but you'll notice the H and the Q have a star, meaning we're at the best efficiency point. So this specific speed is based on performance at the best efficiency point, because hopefully that's where we're operating the pump. So you'll notice those stars are on the H and the Q, and so therefore they're also on the coefficients. Now, the problem with these quantities as they sit right now is they involve diameter. Well, we don't know the diameter yet. We're trying to figure out what the diameter is or how big the pump is. So we would actually like to have a quantity that doesn't have that D in it. So the whole purpose of what we're about to do here is get rid of that D. So again, just this note that these are at the best efficiency point. That's what the star is. Well, remember a thing that we are allowed to do in dimensional analysis. We can take any two dimensionless groups, and that's what we have here, and we're allowed to raise them to whatever power we want, and we're allowed to multiply them together or divide them to form new dimensionless groups. Because those two operations, raising a group to a power and multiplying two groups together or dividing two groups one by the other, doesn't change the fact they're dimensionless groups. So we can form a new dimensionless group by doing that. So we can do that here in such a way that we eliminate the D from this new group that we're forming. So how do we do that? Well, we take the capacity coefficient, which is this bottom one, and we raise it to the 1/2 power. and we divide it by the head coefficient raised to the 3/4 power. And if we substitute in our expressions for CH and CQ, we can see what that's going to do. And so that's all we've done here. So just substituting in for our capacity coefficient, Q over ND cubed, and substituting in for our head coefficient, GH over N squared D squared, you can see what's going to happen here. We have a D to the 3/2 here, and we have a D to the 3/2 here. So the diameter is going to cancel out of this. And what we have as a result is NQ to the 1/2, GH to the 3/4. Now this quantity, this new dimensionless group, is called the specific speed. That's what we've been after here. And notice that it doesn't include the diameter of the pump. It includes those three things that we said we knew going into our application: the speed that it's going to run at, the flow that we need, and the head that we need. And of course G is also in there as a parameter, but that's no problem. We know what that is. So this is the specific speed that we're interested in. So for our particular application, we put all of those known values in there, and we get a number for this N sub S, the specific speed. And then when we go pump shopping, we look for a pump that has that specific speed. So the specific speed will be a characteristic of the pump. And if we match the pump we buy with the specific speed we calculated from our application, we'll be getting a pump that will end up operating near its best efficiency point. That's the whole idea behind this. Now, a little bit about the notation here. So the specific speed is N sub S. And you'll notice that I have a primed on here. That's because this specific speed is a purely dimensionless number. We started off with two dimensionless groups. We combined them together, so this is still a dimensionless group. However, this is not how specific speed is typically calculated in industry. It's the same idea, it brings in the same quantities, but usually this is not calculated using a dimensionally consistent set of units. So if we calculated this with N being radians per second, Q being meters cubed per second, G being meters per second squared, H being meters, this would be a truly dimensionless number. But typically those are not the units used in these quantities. The actual specific speed that you'll encounter in industry is calculated like this. So notice this is still a specific speed, but I've dropped the prime off of there because the units of this don't cancel out. They're the same quantities, so the speed is put in revolutions per minute, just because that's a more convenient form for the units. That's what we're typically working in. The flow rate we're interested in is in gallons per minute, and again, that's typically the units used for flow rate, and the head is put in feet. And notice G doesn't even appear in it because G is always the same, so they don't even bother putting it in the calculation. So when you calculate specific speed like this, it actually does have units, but you just need to be careful that the technical data for the pumps you're selecting have calculated specific speed in the same way. And this is the conventional way to do it, so that will likely be the case. So there's a conversion between these two. If you take a look at all the conversions that are required to make this truly dimensionless, then if you do happen to calculate a truly dimensionless specific speed using that, and you want to get this more conventional specific speed, you multiply by this 17,182. So you can switch back and forth between the two of them if you need to. Now let's take a look at this. Remember that we said that some pumps work well at high pressures and low flows, and others work better at low pressures and high flows. Well, those two things translate into large and small specific speeds, because notice we have Q in the numerator and we have head in the denominator. So low specific speed, a pump that has a low specific speed, is good for high head and low flow. So high head and low flow. whereas a pump that has high specific speed is good for low head and high flow. Now a little bit on why this is called specific speed. Notice that we have speed in the numerator here all by itself, no power or anything. So you could think of all of this other stuff as a way to normalize the speed. And so specific speed is really a dimensionless speed. That's where the name comes from. But it's a pump selection parameter. Now let's take a look at typical specific speeds for different designs of pumps. So this is another figure out of your textbook, and what it's showing is a single impeller blade for a whole bunch of different pumps as we go from this end, which is really pretty much a purely centrifugal pump. So notice the flow would be coming in here, turning, and for most of its trip it's traveling in the radial direction. So that's a centrifugal pump, and it's labeled as such here. So that particular impeller design has a specific speed of 500, and it turns out that's a relatively low specific speed. So if you had an application and you knew the Q and the N and the H, and you put it in there and you turn the crank and you got 500 out as your number, that would tell you you should be selecting a centrifugal pump with an impeller that looks sort of like that. Higher specific speeds, if we go all the way to the other end of the spectrum, so here's specific speeds up in the 10 to 15,000 range, and that is almost a purely axial flow pump. Now they've labeled it here as a propeller pump, and that's really what an axial flow pump is it's a propeller in the fluid. So the flow is still coming in this way, engaging with the blades, but there's very, very little radial motion. It leaves in the axial direction as well. So this is the axial direction, so that's an axial flow pump. And that will have a very high specific speed. So high specific speed means big flow rate, small head. So these are really good for high flow rates and low heads. And of course, there's a whole spectrum of pump designs in between, where there's a combination of axial and radial flow. So these are good examples of mixed flow impellers, where there's significant motion in both the radial and axial directions. And the specific speed reduces as we go back here closer and closer to a purely centrifugal pump. So in summary, the specific speed is a pump selection parameter that tells us what design of pump we should be selecting. And then once we've picked a design of pump, we can use the scaling laws to figure out how big should it be. Should it be a 10-inch impeller, 14-inch impeller, 20-inch impeller? Just how big does it have to be to achieve the performance we require?